So when we're looking at relations and we're talking about linear versus nonlinear, there's a lot of things that we have to remember from grade 9. But first, just looking at a relation is a set of ordered pairs. So it's a bunch of pairs that we're putting together. Remembering that an ordered pair is always going to be x and then y. So we can either represent this as a sentence, so the number of people buying ice cream is related to the temperature, a table of values where we have something like an x and y chart, so 0, 0, 1, 1, 2, 4, 3, 9, a graph, a set of ordered pairs where we've got a whole bunch of ordered pairs together, so like this, or an equation like y equals x squared or y equals 4x plus 1. So those are all different ways we can represent a relation. Now, when we're looking at a relation, what we have to recognize is that there's a domain, which is the set of the first elements, always the x, okay? They're always independent, okay? And then there's the range, which is the second element, or the dependent, the y values, okay? Now, this could always be different letters. It doesn't have to be x and y. Could be A and B, M and N. It's always the first letter alphabetically is the domain, the second letter alphabetically is the range, and it's going to be independent variables. Now a function is is a relation in which no two ordered pairs can have the same element, okay, or the same first element, excuse me. So that means for every x value, there's only one y value. Now, all of the x values could have the same y value, but none of the y values can have, multiple y values can't have the same x value. Okay, now we can look at this through a vertical line. So if I were to draw a graph, the easiest way to do this is if I drew a line like this. Now, if I put a vertical line on the page, I'll put it in a different color here. If I put a vertical line on the page, this never is going to touch another part of that graph, that diagonal line. Okay, but if I were to draw a graph like this, and I drew, let's say, a circle or an oval or whatever that shape is, and I drew a vertical line, well, it hits the graph there, and it also hits there. So this fails the VLT, or the vertical line test, and then that would mean that this is not a function. A function would never fail the vertical line test. It means all x values have their own unique y value. Okay, so let's look a little more. So if we wanted to state the domain and range of these values. Now with ordered pairs, we can state our domain. So we do these, I'm gonna make it look nice. We do these fancy little brackets for our domain. Okay, now all we're doing is looking at all of the values of x. So we've got -3, we've got -1, 0, 2, and 3. For our range, and we'll put the fun brackets, for our range, we've got, and you don't have to put these in order, I'm just doing it because it looks a little nicer. You should try to put it in order, but sometimes these ordered pairs get so big that you would never be able to do this. It would take you forever. So all I'm doing is looking at my x and then my y. Now if I look, none of my values have the same x. So I don't have two x values for a different y. So then therefore this is a function. Okay, there's no repeating x values. Now, if I go over here and we do the same thing, we've got our domain and range. Our domain over here is going to be 0, 3, 8, and 15. And our range is going to be -2, -1, 1, 3, 4. Now there's kind of two ways that you can see this is not a function. first, I have more values in my range than I do my domain, but also I can see right here and right here, I have a repeat of x equals 0. Okay, so that's not a function. You can't have the same x value for our y's. All right, if we were to look at these, so this one, these two graphs are the exact same. So what I'm going to do for the second one is, let's see the third one. What I'm going to do for the second one is I'm just going to scratch it out because it's literally the exact same as this one. So if we were looking at this, we're going to do what's called interval notation for our domain and range. Now in the first example, we just stated our domain with all of the values. Now with interval notation, there's a few things that we need to know. Okay, and we're going to kind of go through this as we go, but our brackets matter. Okay, now the type of bracket we use matters. On the last function, when we were putting those in, or sorry, the last relations, our domain and range were just points. So we were picking the individual point and saying, here's our value, it has to equal to one of these. But on these graphs, we know that they go on forever, and I could pick, if I wanted to zoom way in here, I could pick a point right here that's like 0.000001. So we need to include that too. So when we're talking about that, what we're actually going to say is that these brackets, round brackets, are everything up into that point. So a round bracket, and this is gonna make way more sense when we start doing these examples, and we'll do a lot more of this in grade 11, but round brackets do not include the number. Okay, so it's infinitely close to the number, so if I did something like this, so this would say that my domain is between 4 and 3. It's everything as close as I could get to 4 and as close as oh, that doesn't actually make sense. Let's make it actually -4 and 3. We always go smaller to bigger. So 4 to 3 wouldn't have made sense, but we can go -4 to 3. So this is saying everything right up until I get to -4. So -3.99999, as many nines as you can think, but it'll never get to -4. Same thing with 3, it'll get all the way up to there, but it'll never get there. Now if we do a square bracket like this, this does include the number. So if I was looking at this and I said 0 to 2, this would be from 0 all the way to 2, including those numbers. Now when we're doing the domain for a parabola or a quadratic, which is this, and this is going to be our whole unit, what we're going to be doing is we're going from -infinity to +infinity. Now if you put square brackets on this, I wouldn't get upset. I've seen it both ways in textbooks. A lot of the textbooks that we use have round brackets, so that's why I have round brackets. Now that means that it can go all the way to -infinity and all the way to +infinity, but because we can never actually get to that number, we put round brackets. But because this graph is going on forever, it's putting an arrow that way and an arrow that way, my x values can go forever. Technically, I could just keep going up and I would get to those values. I'd keep going. My range, however, it does have a limit. It can only go down as far as this line. So, and it includes that line. So what we're going to say is we're including -3. Our value is at -3, and we're going to go all the way up to infinity. Okay, we're including -3 and going up as far as we can go because those lines are there. Okay, now if I look at this, oh, sorry, we've got to say that this is a function. So I'm going to just make a little, so this is a function. because if I were to put a vertical line on this, anywhere on the graph, it's never going to hit 2 spots. So it passes the vertical line test. Okay, now if I look at this one, right away I can see that this is not a function, because right there it would fail the vertical line, so not a function. And if we did our domain and range, because these are points, we're no longer going to put our brackets. We're going to just put each point. So we've got -3 for our domain, that's all our x's, -1, 1, and 3. Now this looks kind of like a sideways parabola or quadratic, the one we were just looking at. Whoa. But it doesn't, we don't know because it's not actually connected. So this goes -2, -1, 0, 2, 3, 4, and 5. Wow, that's kind of some weird numbers. All right. And then finally, if we're looking at this, just kind of review from last year. I'm just going to make my pen just a little smaller. If we have a linear relation, what we're looking at is things that are like y equals mx plus b, or if we had something that was like ax plus by plus c equals 0. And these are things that we've already considered. Now a non-linear relation, it could be literally anything that has an exponent that is not 1 on our x values. We're not really going to deal with exponents on our y. We could deal with something like this, which is really just a 1/2 exponent. And the other thing that we could look at is if x is in the exponent. Okay, so when we're looking at a table of values here, our rate of change is our slope for a linear function. And for a nonlinear function, we don't really have a rate of change that we can deal with. Okay, it's not going to help us figure things out in this sense that it's not the same as the slope. So it helps us find our a value or our differences, but it's not the exact same. So if we were looking at a linear function, if we just had 1, 2, 3, 4, 5, 6, we could have like 3, 5, 7, 9, 11, 13, where it's going up by the same number each time. So here it's going up by 2 each time, and 1. So in this case, our slope would be 2 over 1, or 2. Okay, delta y over delta x. Here, if we look at it, if we went like 1, 2, 3, 4, 5, 6, and we were just doing something like x squared, we'd get 1, 4, 9, 16, 25, 36. So we're still going up by 1 each time on the x's, but here 3, 5, and you can see already that it's not similar, but there is something unique about it. So we go up by 3, 5, 7, 9, 11. If we were to look at the next one, it's 2, 2, 2, 2. So the second difference is actually equal in this case, and that tells us it's quadratic. Now the appearance of a linear graph, obviously, is just a line. It could be like that, could be like that, could be like that, also could be like that. Just has to be a straight line. Now, what we've done here is we've done something like this, which is just a quadratic. Could also be like this. Just anything really that's not a straight line. Okay, and that covers this.